So our next speaker, a guest lecturer at the University of Oxford, where he graduated and also taught OU computing services. He worked in data science since 2013, most recently as a data science tech lead at filtered.com and as R&D data scientist at Mudano. Jakub is co-author, as we announced earlier, of GANs in Action by Manning Publications. He also designs and teaches data science courses at the University of Birmingham, private companies, and as I mentioned, is a guest lecturer at the University of Oxford, speaking today on the overview of generative adversarial networks. Please welcome Jakub Langr.
Hello. Thank you so much for the wonderful introduction, and thank you everyone for having me. It's a great honor to be here. Actually, this is not my first time in Romania. I have this very happy picture when I was mountain climbing. Hopefully, you'll have as great of a time in this lecture as I had when I was in Fagarash. It's good to be back. Yeah, we kind of went through this, so I won't really go into this. However, there was a book signing. If you missed it, I'm sorry, but there is still a chance for you to get an e-copy of the book because I have 2 codes from the publisher for the e-book. So if you want and are interested in something like that and find today's presentation interesting, then feel free to tweet or post something on LinkedIn and tag me, and I'll pick 2 winners and give you a free copy of the ebook. So unfortunately, it's not as cool as a physical copy, but there's hope. Let's kick this off. So basically, I just want to kind of get a sense of the room before I dive into something that's either so obvious that everyone is telling me to move on, or kind of so advanced that no one's really following. So can I just get a show of hands really quickly? Like, who here has at least basic understanding of deep learning? Like literally just have, looked at some tutorials. Now keep your hand up if you have at least trained copy-pasted code from somewhere. Okay, okay, good. Now next, keep your hand up if you know what a GAN is. If you have at least heard of it. Okay, good. Has anyone here trained a GAN from scratch? No. Okay. So that's good. I think there's still kind of some division. So I'll probably kind of try to keep it mostly technical, but I'm also more than happy to keep it interactive. So if you guys have any questions or want to have talk about something in a bit more detail, then happy to take a question. Probably don't want to derail it completely, but that's happy to interact. Really brief introduction to supervised machine learning. So this is obviously super rushed, but what do we actually do when we train all those wonderful models that we talked about most of the day? Well, so we have some sort of data. We extract some feature vectors. In case of deep learning, you generally have a neural net do that for you. And then you have some machine learning algorithm that basically learns the mapping between those labels and this feature vector or the raw documents. And that basically gives you your trained model. Now, on inference time, in order to make this model actually useful or do something, you take a new sample, new image, document, whatever it is. You extract the same feature vector or run it through the same neural net. And then based on this predictive model, you just ask it, okay, what's the label, right? So that's relatively nice and easy. So now, obviously, that's not the only paradigm. There's unsupervised learning. So, most of the generative adversarial network lives in this unsupervised world, which, arguably is more exciting because there's tons and tons of unsupervised data on the internet. There is maybe not so much labeled data. You need to create that in-house. So there's a lot of sort of excitement about the possibilities that unsupervised learning can provide. Obviously, it is still machine learning. So as you can see on this MNIST model, which is the hello world of computer vision, you kind of start with a really bad sort of approximation, and then you work your way into something that actually looks like handwritten digits. But there's obviously, with a new frontier come new challenges. So you need to have things like, okay, how how well are we actually doing? That's a tough question, because now you need to quantify how realistic a particular sample is, right? In a case of supervised machine learning, that was fairly trivial, because we can say, okay, did you get that answer correct or not? But how do you quantify, what is the quality of a digit? It's very hard. Or, even more complex imagery. And so, obviously, ultimately, we're trying to generate examples that look like they came from some original distribution, using some learnable function that generates new data, some learnable parameters that sort of we encompass in some generate function. So, why is this generative process kind of complicated? Well, the distribution itself can be quite complicated. So this is like a principal component analysis of the MNIST digits that we just saw on this slide. So if you look at the 768 dimensional vector that creates those 28 by 28 images, and then projected using principal components down to 3 dimensions, this is what it looks like. And this doesn't really tell anything to anyone. And it's very hard for humans to actually reason about such high dimensional spaces. It's very hard for us to say, okay, somewhere here are good digits and somewhere here are bad digits. Well, we can see that the PCA has done kind of like, okay, so zeros are kind of here and then nines are somewhere there. So it tells us something different, but it doesn't really tell us how good those digits are. How do we consider those good samples or bad samples? Hard to say. And obviously this automatic evaluation is super important as we train, because we cannot have humans look at every single sample. That kind of defeats the purpose of machine learning in the first place. So obviously GANs are an approach that kind of gets around this problem by saying, you know what, let's kind of cut the human out of the loop, and let's just implicitly try to model this high-dimensional probability density function, this high-dimensional space, and where the good samples live. But we obviously that obviously means we don't get some neat analytical closed-form solution. So we don't get some formula that we can easily write down, this is how you generate a good MNIST digit. So how does machine learning generation work? So you take some sort of input vector for sort of inspiration, some sort of latent seed, so that you don't generate always the same digit. You have some sort of decoder or generator, or some some generative model that you for now, let's just assume that was given to us, and then you get some output, right? So basically, all that's necessary is that we have some sort of inspiration, some sort of random seed, latent vector. We run that through some learnable function, and we get an output. So what does this look like in GANs, so generative adversarial networks? So if you walk through it word by word, you kind of get already a pretty good understanding. So first of all, generative, obviously, because they generate; networks, because there's 2 of them; and adversarial, because they compete against each other. So there's a network called the generator, which is this generate function that we've been talking about, and there's this network called discriminator. So the generator takes, again, this latent seed and tries to create something that looks like an MNIST digit. And then the discriminator effectively just gets intermittent outputs from either the real data distribution or the generator, and is trying to tell which is which. So effectively, we have abstracted this notion of the evaluator, right? How do we tell how good we're doing, to this discriminator network, which all it's doing is binary classification problem. It's effectively, that part is effectively supervised. What's not supervised is the generator, who needs the feedback from the discriminator to basically know how well it's doing. So another way to think about it is we have some sort of neat overview, is that, well, generator is a vector of random numbers that it gets and converts that into some samples that look as realistic as possible. And then the goal is to obviously generate data that's indistinguishable from the rest of the training set. And then the discriminator is basically gets input from 2 sources. Either it gets an input from the actual training set, the actual images that we're trying to model, or it gets the fake images coming from the generator, right? And then basically it just says the likelihood that the sample is fake. So a neat analogy that you can use to think about this, if this is still somewhat confusing, is just you can think about it as some sort of forger, right? That is trying to come up, or an amateur painter that's trying to come up with some good painting. And then you have a detective that's trying to tell the two things apart. It's trying to basically, say, okay, this is a real painting of Da Vinci, and this is not, right? So through this iterative process where both networks start out quite bad, you over time actually improve the relationship of the two. And as a result, the generator actually learns to produce samples that are quite reasonable. So that's kind of what we're telling here in a more sort of technical, slightly more technical language, which is like, the classification error from the discriminator gets propagated all the way to the generator, and equally the discriminator gets punished when it gets fooled by the generator. So like that is another way of saying, like, there's this loss function, which is the original loss function in the original 2014 paper, that just kind of says, like, hey, look, like, we're trying to basically, as a discriminator, you're trying to distinguish the real samples from the fake ones. And I'm not going to go through all this, but like the key thing here is that in the original paper, the generator's loss function is literally just the opposite of the other one. So they are very obviously like adversarial in the sense they compete. So for those of you who like game theory, this is kind of reminiscent of Prisoner's Dilemma, when one has to sort of like where both of them are kind of competing against each other, and effectively there's some analytical solutions for some of the simple problems. Yeah, so this is something that combines GANs and Metropolis Hastings, but I think main point that I tried to make here is that basically it's this, almost like you have some complicated loss function, and you have like two people that are like tied to each other on a leash or something, and one of them is trying to go downhill and the other one's trying to go uphill, and that's how they kind of compete in this like super high dimensional loss space. So in the end, people realized that actually, and I think this was already a contribution of the first paper, that there's a better way to that has some sort of improved numerical stability. So people eventually said, let's not worry about making it nice and game theoretical, but let's actually put some like something that allows us to train much better. So they replaced the other term. So now most GANs that you see don't have all these neat proofs that could follow if you just stuck in game theory. So now instead you have what's called non-saturating loss. But okay, so that was a lot of sort of background and a lot of math to something that could be quite dry. So why do we care about this? So generative modeling obviously is a very challenging problem, and especially the general case, having a framework that can generate as diverse data as what GANs have been able to generate. So that's audio, text, video, speech, all sorts of graph networks, highly structured data, medical imaging, like basically anything that you can think of, GANs have already sort of managed to replicate. So this is like arguably the first general purpose machine learning framework of learning very complex pieces of data. So in 2016, this was kind of the state of the art. This was the best what we could do. This was produced by another technique called Variational Auto-Encoders. And that was kind of how well we could do up until that point. Now, in 2017, this paper came along from NVIDIA, where they managed to generate like full HD resolution faces in that, in incredible diversity and an incredible level of detail. So all of these people like don't exist. In fact, there's a website called thispersondoesnotexist.com. And if you go there, every time you reload, it generates a new person. And that person that uses a similar architecture is not this anymore, because this is so 2 years ago, so no one really cares at this point. People like produce almost instantly better architecture. So in 2018, architecture called StyleGAN, which is kind of the state of the art now, came out and produced like even higher resolution than this. So this is quite a short journey for a machine learning field, where most machine learning has roots really falling back to like the 90s, 80s, and so on. Whereas the very first paper in GANs has been actually released, like at the NIPS 2014. So this was, so December 2014 was like the first time that this paper was presented. So how have we kind of gotten from, like, where have we gotten from there? So one of the most interesting applications and one of the things that I use mostly in the most in my day-to-day work is called CycleGAN, or at least the basis of which. Now, again, CycleGAN is so 2017, so no one uses that anymore. But CycleGAN was a really fascinating paper because how generalizable that architecture has been. And all that it needs is a bunch of pictures in one domain and a bunch of pictures in another domain. So a domain you can think of as like, a Monet painting and a real photo, or as photos of zebras and photos of horses, or summer and winter, right? And is able to actually translate every single image how it would have looked like in the other domain, right? So it says, okay, well, what would this Monet painting look like as a real photo? Or what would these zebras look like as horses? Or what would this Yosemite Park photo look like in the winter? And you can kind of translate in amongst so many fascinating domains that without any need for pair data, right? So you don't need to have the equivalent picture that, actually go back, reconstruct the scene that Monet would have painted in like the 19th century and then take a picture of it, and that's how you get your training data. That's effectively impossible. All you need is those two domains, and as long as they're sufficiently distinct, it will create these like really interesting pieces of imagery, because it can generalize what it sees in the one domain, right, having a lot of snow, and the other one having a lot of green, and so on. So it's quite intelligent, and I'll show you some examples that I've done afterwards. So this is kind of what I was trying to explain with the two domains. So typically you have one generator going one way and another generator going the other way. So this is a more complicated architecture. We go through it in a lot more detail in the book. And there's an entire chapter on it. So of course I'm trying to give like a super high level overview. But basically it's going back with this notion of a cycle. So you start with the original, like let's say, winter image. You make it into a summer image, and then you make it into a winter image again. Now, why would you do that? Well, it allows you to then measure the loss of like this reconstruction. How good is it compared to the original input, right? So you can measure this cycle consistency loss, and that way you usually get a sensible mapping. There's a couple of other tricks to make that work more consistently, but that is the general idea, right? So you basically like translate twice. It's almost, another analogy could be like, think of translating from English to Romanian and from Romanian back to English, right? You should ideally get the same sentence. So then you can measure the difference, and that's how you know how good or bad your two translators are, right? So for example, like one of the, at every step, you will also get a discriminator. So effectively what you get here is two sets of generators and two sets of discriminators. So you have a discriminator for the A domain, so for like winter or apples, and for the B domain, which is oranges or whatever. On the projector it kind of looks the same, but anyway, it's like the important takeaway here is that you get two sets of each generator and discriminator. This is super not right. So actually, all of the like, if you can faintly kind of make out the background, I should really make that brighter. Some of these images that you see, they're all of my translation slides have generated images only. Like all these images are, even if you kind of can see the eagles here, that they have all been generated by this next architecture that I'm going to talk about, that their author decided to call Big GAN. So Big GAN is really interesting. I won't go into the technical detail, but there's a fascinating artistic application that one of my friends wrote as a sort of free service for artists for them to try explore the latent space of Big GAN. And because Big GAN is such a rich and powerful model, like it can generate these absolutely amazing pieces of art in relatively high resolution. It's not as good as StyleGAN, but it's pretty impressive. And every time you generate an image, you can sort of take the latent vector that generated that image and dissect it and add more or less of another image. So effectively like crossbreed this image and this image, hence the name breeder. And then you could get what would the average of those two pictures look like with some semantic logic in. So it doesn't just naively do half pixel values of both, but it kind of tries to imagine what would that actually look like. So you can sometimes get these really trippy animations of like crawling through the latent space and basically like, you know, dogs turning into tennis balls, but like in a really smooth way that you can't really tell when it's still a dog and when it's still a tennis ball. It's very confusing, but I'm sure it's great when you're in an altered state of mind. Anyway. That's something to do on Friday afternoon, you know? Now in a little bit more serious note, adversarial examples is something that came, that came with GANs, but it's not exactly the same kind of underlying set of techniques, but it exposed this really, really important problem in computer vision that I think not nearly enough people talk about, especially in mission critical applications. I was kind of surprised that some of the like really sort of high stakes government suppliers don't actually know about this, and that's kind of terrifying. So what adversarial examples are is using a similar kind of concept of like the adversarial training, which effectively means that for those of you who have been, for those of you who have been in the tutorial for TensorFlow yesterday, remember about stochastic gradient descent and how we use that to train. So this happens when you abuse the training mechanism, when you abuse stochastic gradient descent to basically give you rather than minimizing the error, you maximize the error. And it turns out that this is actually really easy to do. So if you have a picture of what we would hopefully all agree is a panda, and you add like usually like tiny fractions, like thousands of or tens of thousands of this noise, of this specially constructed noise, you can get the most pretty much all computer vision classifiers to misclassify this as, say, a gibbon with much higher level of confidence than the original panda. And it's just that this noise is so specially constructed that it actually breaks the classifier. The problem was worse still is that this generalizes quite broadly. So these are actually printed images of what we hopefully agree is a washer, right? But then this one is classified as safe, and this one is classified as safe with even higher confidence than the original washer. So it's quite a bit of problem because these are all printed. They have not actually, these are not the raw images. So the noise is so robust that it transfers even after changing medium, which is a bit of a problem when you think about a deployed computer vision system to maybe check, you know, whether through like facial recognition, whether the person is allowed to work in this office or not, like whether, you know, they have access to some secret lab that you might have in your company, or, you know, like whatever it is that people might care about. But this is like quite a bit of problem, or at the border, right? Like all these things start to, like with these adversarial examples, start to kind of get really complicated. Some people are actually, good application of this is that some protesters are using this in Hong Kong as well to like get around the facial recognition. But, you know, also like problem for some other systems you might you know, think about the security kind of going back of the previous speech. Yeah, so I mean, I'm probably gonna skip this in the interest of time. This is adversarial noise that I literally just randomly sampled, and even reasonably good classifier that was like the state of the art, the best one in 2014, actually gets most random noise wrong, which is an interesting like facet. So, and it's actually really easy to adjust completely randomly sample, like literally np.random.sample. Sorry, np.random.nnorm. Even that noise basically fools the classifier into thinking it's something. So that's something to worry about. In actual fact, like there's some people who go the other extreme and say like, therefore all computer vision is invalid. I don't think that argument is, super strong. I think in some certain mission, like certain security application, you should really think about it. By and large, not that big of a issue. There's a really great paper from Google that Ian Goodfellow is an author. I think it's in the references where they go into this in a lot more detail. Really quickly, practical applications. So there's lots of interesting things about like design at scale, or sort of generating these translations. So especially like if you think about CycleGAN, one of the other applications the authors did in the paper was like translating satellite imagery into Google Maps like looking images, like clear sort of city lines, and then back again, or the other way around. Again, like summer to winter. Generating lots of design logos. This is not an architecture we covered, but there's something called Discovery GAN or Disco GAN for short. It's also a little bit outdated now, but these things move so fast, it's hard to keep up. So this is an example that I did. I mean, if you can kind of see, this looks like some bad video game, right? And this looks like almost photorealistic. So yeah, I don't know if you can fully appreciate. Maybe I'll put the slides online, and then you can probably look at that a little bit more. So that's one of the interesting applications where you can basically create synthetic content that looks more realistic, or if you don't have enough training data, again, you can transfer that into something that looks more realistic. This is a paper that actually hasn't been presented yet, but it's already online, where people take like different seeds from like different starting images, take a semantic map, and then use basically to synthesize every single frame in a like car driving video. So you can kind of like say, now I want to drive in Berlin, or now I want to drive in LA, or whatever. And then you can reconstruct the same scene using the semantic map as that driving sequence, which is kind of cool. So this is also like medical applications. So Kiron Medical uses this for like sort of helping diagnose cancer when they don't have enough cancer samples. Their machine learning models obviously don't work super well, but they still need to classify, diagnose those patients that have. So they use GANs to basically synthesize new cases of those rare diseases so that their performance is better, right? Because then the classifier learns, okay, what does this roughly look like? So that's an interesting application when you have certain like rare cases, but you should really get right. There's some work being done in 3D. It's still relatively immature in 3D, but you can already see they can generate like quite sensible images of chairs and things, and you can kind of like design it based like by playing around with the latent space. Yeah, I mean, there's some companies use it for like usability studies and things like that. Obviously, style transfer. Some more work in CycleGAN. So this is like kind of the last thing that I would mention. So obviously, the growth in GANs has been like absolutely unprecedented. Like I've never heard of an academic field that went from like basically the first paper to like now over 10,000 citations of the original paper in basically like 4 or 5 years. Lots of AI sort of like celebrities kind of say that this is an interesting technique. Whether you don't want to believe them or not, sort of up to you. But I think the one thing that I found really fascinating is that when you look at the amount of the cited impact, it's about 2.5x the impact of TensorFlow itself, which is basically the platform that Google open sourced, right? So it's like where a lot of GANs would be written in either TensorFlow or GAN, or TensorFlow or PyTorch. So that's kind of interesting. But the reality is that the business applications are still young. But that probably also means that this is a consequence of the technology just coming out not too long ago. So this is still like at the very cutting edge. So there's some references. Yeah, the book, and if you want to talk to me about synthetic data, please do email me, because that's something that I'm really passionate about and I'm definitely keen to explore. The book is now released. You can get it on Amazon if you're interested. We try to write it at a level, if you read like Chollet's book, like Francois Chollet, then you should probably be able to pick it up. Yeah, so that's it. Thank you.